Hi, my name is Fahrettin Gökmen. I am a retired aircraft maintenance technician. In this video, contents related to telemetry data and analysis will be shared. First, the concept of the telemetry and the types of telemetry data will be discussed. Then the tools used for telemetry analysis will be introduced. Subsequently, UAV component data will be addressed to interpret telemetry data. Advanced telemetry analysis techniques will be explained, and practical suggestions for interpreting telemetry data will be presented. The telemetry system is the backbone of the drones, communication and data flow, and encompasses the hardware and software components responsible for transmitting vital flight data between the drone and the ground control station. The main components are bidirectional communication modules and antennas. Data collected by sensors such as altitude, speed, GPS coordinates, and the battery levels is processed by flight control computer. The flight computer analyzes and formats this raw data. Telemetry modules transmit the data received from the flight computer to ground station using technologies such as Wi-Fi, cellular networks, or radio frequency antennas ensure reliable and efficient signal reception and the transmission. Drone telemetry is the bidirectional data exchange between an unmanned aerial vehicle and the ground control station. This allows real-time data about the drone and enables remote control. Telemetry data provides real-time data about the drone's position, status, operation, performance, and environmental conditions. With real-time data flow through telemetry, potential issues can be detected early, and preventive measures can be taken. By monitoring battery levels and other parameters, flight time can be optimized. Telemetry software platforms are essential tools for monitoring and controlling drone flights. These platforms offer a user-friendly interface for visualizing flight data, adjusting parameters, and executing pre-programmed missions. Popular telemetry software platforms include OpenPilot, DroneCode, PX4, and ArduPilot. Telemetry data storage systems are important for preserving flight records, sensor data, and video footage. Technicians or operators can identify and resolve potential issues before they occur by analyzing real-time telemetry. Common troubleshooting techniques include monitoring key parameters such as battery voltage, motor RPM, GPS signal strength, and sensor readings. Unusual fluctuations or anomalies in these values can indicate fundamental issues such as faulty sensors, motor failures, or communication interruptions. Additionally, examining historical telemetry data, etc., flight logs after flights can help identify recurring issues and trends. Telemetry data is categorized into various types, including position and status information, flight data, power system data, motor and SAJ data, environmental data, payload data, and radio control data. Flight data includes information such as altitude, flight speed, GPS coordinates, and heading. Power system data contains important information such as battery voltage, current draw, power consumption, and remaining battery capacity. Motor and ESC data track motor RPM and ESC temperature and motor temperature, while environmental data covers ambient temperature, barometric pressure, and current wind speed and direction. Payload data allows monitoring of camera status and gimbal status positions, while radio control data ensures signal strength, control inputs, and fail-safes. This data provides valuable information to drone operators and technicians, enhancing flight safety and efficiency. Tools used for telemetry analysis process this raw data to perform tasks such as visualization, statistical analysis, and modeling, providing valuable insights to the user. Ground control station software like Mission Planner and the Q Ground Control provide live data streaming during flights, while software like Mail Explorer and Open Telemetry offer detailed analysis of recorded telemetry data. Additional programming languages like Python and MATLAB are useful for customized analysis. UAV technicians should be careful when reading altitude and airspeed data. For example, sudden altitude change may indicate potential motor issues or strong winds. Additionally, inconsistent airspeed may signal possible incorrect sensor readings. Sensor failures, pitot tube failures, GPS failures, or propeller or motor issues. When interpreting data, it's important to plot altitude and airspeed graphs during the flight. The graphs should be checked for gradual change and examined in detail. Detecting sudden climbs or altitude losses helps identify issues at an early stage. Reading GPS data also requires expertise. Abnormal elements include GPS deviations, sudden jumps in positions, and decreases in the number of connected GPS satellites, as well as high values of horizontal deletion of precision during normal flight. Pitch and roll angles are usually within the 45% degree range. Excessive oscillation may indicate calibration issues, while sudden angular change provide insights into hardware failures or external forces. To interpret the drone status data, it is necessary to monitoring the data during the flight. Smooth transition and stability are important while hovering. If there are unusual sudden increases or oscillation in hover mode, they should be identified. In battery data, the normal situation is regular voltage drop and the regular current draw. However, there may also be some abnormal situation. For example, sudden voltage drops indicate a potential battery issues, while an unusually high current draw may indicate motor or ESC problems. To interpret this data, it is important to plot voltage and the current graphs over time. Additionally, evaluate the power consumption found by multiplying voltage and current against the standard values determined for the drone model and flight profile is a good method for detecting potential anomalies. When checking motor and ESC data, unequal motor RPM values between motors and indicate possible propeller or motor issues. Additionally, high ESC temperatures indicate a potential cooling problem or overloaded. To interpret this data, first compare the RPM values of all motors. Motor and ESC temperatures should be plotted over time, and these graphs should be compared with the flight maneuvers and power usage. In UAV radio receivers, the normal situation is consistent radio signal strength, responsive and sensitive control inputs, and no control latency. Abnormal situation includes signal interrupts or weakened and delayed or unresponsive controls. To interpret this data, first examine the received signal strength indicator curves during the flight. Then analyze control inputs by comparing them with drone behavior. Finally, checking if there is an issue with the binding of the receiver and transmitter helps identify potential problems. Advanced telemetry analysis techniques are of great importance for UAV technicians. These techniques include cross-correlation of data, vibration frequency analysis, abnormal detection, and power efficient analysis. For example, comparing altitude change with motor RPM helps determine cause and effect relationships. For cross-correlation analysis, Statistical software or custom scripts should be used for search for strong correlations between different data sets. Vibration frequency analysis is very useful for identifying oscillations and vibrations. Vibration frequency analysis can help diagnose PID tuning issues or mechanical problems. Using fast Fourier transform compared to dominant frequencies detected by the accelerometer with non-drawn characteristics. PID, which stands for proportional integral derivate, is a control algorithm that ensures a system reacts and maintains as desired value. The proportional term represents for error in the system, which is the difference between the desired value and the actual value. The integral term considers the sum of errors over time, helping eliminate persistent errors in the system. The derivative term considers the rate of the change of the error, preventing the system from overreacting. Anomaly detects uses machine learning algorithms to identify unusual situation, isolation, forced or one-class SVM algorithms can be used to create normal behavior from historical data and detect anomalies. Finally, power efficiency analysis calculates and monitors power efficiency over time. By tracking power efficiency values, such as watt-hours per kilometer, across multiple flights, trends or sudden change in efficiency can be identified. When interpreting telemetry data, it is important to record and analyze telemetry data from known trouble-free flights. This data can be used as a reference point for future comparisons. Analyzing telemetry data after each flight helps detect changes that may indicate wear or failure. When interpreting data, it is crucial to consider environmental factors, flight mission profile, and flight maneuvers. By conducting a holistic analysis, look at how different telemetry data sets relate to each other rather than focusing on a single data point. To identify long-term trends, monitor baseline values over time and use prominent data for predictive maintenance and performance optimization. Additionally, keeping detailed records of telemetry analysis, documenting identified anomalies and actions taken is a critical step in preventing future issues. Keeping statistics on the time and causes of failures will provide both convenience and time saving in failure detection and resolution. In this section, we covered telemetry data and its analysis in UAVs. I hope the contents have been helpful. See you in next content. Goodbye.